Hi, my name is Milos and welcome to Element 14 Presents. Today I will be talking about robotarms. This here is a robotarm kit made by Arduino. It is a robotarm that has 5 degrees of freedom. It uses pretty powerful servo motors and it's pretty easy to assemble. One problem about it, it costs around 240 euros. And while the kit itself is really made good and you even get a shield for Arduino so you can easily connect the arm, a power supply and things like that. I thought with the wide availability of 3D printing now, either by people having 3D printers, maker spaces, libraries and such things, I thought how cheap can we actually go and make a pretty decent arm comparable to this. Let's get started. Let's take a look at the robotarm configuration. First, the Arduino arm. We have the base joint, the 3 normal joints and another last joint that's oriented differently, and the gripper on top. For our arm, I want to keep the same configuration, use smaller servos to save on the cost, and also get position feedback using a potentiometer. That means we need to place a potentiometer on the other side of the servo and keep them on the same axis, and we're gonna put them in a 3D printed case enclosure, and that will be our finished module. Okay, now that you've seen how the configuration of this arm goes, let's take a look at the main components that actually make the arm move. Here in the middle, the black thing here, are the servo motors that actually control the robot arm joints. These are hobby servo motors. And here on the outside, I've added potentiometers, so you can actually track the position of each joint as it moves. Servo motors, at least the hobby ones, most of them, work with a potentiometer inside. Let's take a closer look at what makes actually a servo motor, how do we control it, and we'll go from there. So this is a drawing of a standard hobby servo motor that you can see around. It has 3 pins, power, ground and signal. The ones we will be using have a plastic body, 2 mounting holes and a motor shaft. Let's take a look at the inner workings of a servo. So inside it's a normal DC motor with a big gear reduction, and on the output shaft of the gear there is a potentiometer which measures the angle, and a PCB with a controller where we send it the signal and it tries keeping that value. Now there are other fancy servos that have RS485 communication or something else, but these servos that we will be using, they are controlled using what's called PWM or pulse width modulation. So for these servos, we tend to go around 200 to 300 Hz, for example, and for 0 degrees we want a pulse width of 500 microseconds, and for the 180 degrees, we want 2500 microseconds, and that's how we control a servo motor. Okay, so let's take a look at how we will design the module that holds the servo and the potentiometer. First off, I began by actually measuring the actual servo and making a model out of it. The next thing we need to do is actually place the potentiometer, which you can see here. So as mentioned before, we want both the shaft of the motor and the potentiometer to be on the same axis, so that we can use that axis as the joint of the robot. The thing now is that we need to do is design a 3D printed case that can both mount the servo and the potentiometer. The servo motor mounts using these 2 holes here and here, while the potentiometer mounts just with a nut here. So this is the box I designed that houses in both of them. I tried making it as small as possible, but I still wanted it to be aesthetically pleasing, so it's not just a skeleton box but an actual box. And on top of that I added a lid. Okay, now that you've seen the CAD of the module, let's assemble it. First things first, we need to insert the 4 M3 nuts here and cut the threads here. These threads aren't necessary, but I like cutting them to get a more reliable connection. First thing you want to do is insert your potentiometer. I already soldered the wires. Okay, now that that's done, the next thing is to insert the servo motor. The holes on the servo motor are 2.5 millimeters, which is perfect for M3 screws, so I cut the threads again. To insert the servo, you need to fold this cable like this here, a little bit less like this. The next thing we need to do is attach the servo using the 2 screws. Don't tighten it too much so you don't strip the threads. And it's a pretty snug fit, so the servo won't go anywhere. And the last thing when it comes to the mechanical assembly is to add the cover. Okay, so that's the finished module. Next thing we need to do is crimp the connectors. I'll speed this part up. Okay, the last thing to do is to actually put the pins into the connectors. This is the board, the final board that we will be using for controlling everything. This side here is for the potentiometers, and this side here is for the servo motor. So the outside pin, as it goes like this, is for the ground pin, which is the black pin here. Then in the middle is the 3.3 volts, which is the gray wire. And in the end we have the signal wire, which is the middle contact, and in my case that's the white wire. And it clicked into place. That connector is done. Now let's go to the servo connector. The outside pin is again the ground, so that's the brown wire here. That clicked into place. The middle is the power for the servo. There you go. And the last one is the signal wire. And it clicked all into place. So this is a completely finished module now. Let's take a look at another thing, and that's how do we actually attach these arms to the module. To do that, we actually need to use a microcontroller or a function generator. So there's a program on the Arduino Uno running which just turns the motor to 0 degrees, then to 180, and then back to 90. 180 and then 90. So why is that important? It's important so we actually center the servo motor, so we know that the center point is 90 degrees. So this is the servo arm. It has the servo plate that came with the servo motor. I just glued it into place. Everything is exactly 24 millimeters wide. They're the same. So the easiest way to do this is place both on the table. Just push the servo arm onto the module. Okay, and that's how you get the arm attached. And the other one is for the potentiometer. So the potentiometer can't go a full turn, but if you place it like this, you can see that you can get 90 degrees both ways. So that's what we're gonna go. So we're gonna attach it like this. It has a little stop so it doesn't go too far. And to tighten it, you just use a small screw right here, and that would be it. So now if we restart the Arduino, 0, 180, 90. Okay, so you've seen how the segment goes together. Let's now test it out. Here I have a setup for actually recording the movements. It's calibrating now, finding its minimum and maximum position. And now if we move it in a particular direction, like this, and leave it, after the recording session, it will go ahead and repeat that movement. So if we do this for all of the joints on the robotarm will essentially remember what it did, and it will just repeat that. Let's take another look when it comes to the joint design. So this is the joint we've just tested. We're gonna have 3 of them. So we have the servo motor and the potentiometer on the same axis. But what about the base joint and the last joint? They're kind of different in their construction, and we can't have arms on both sides for the joint to be stable. We need some kind of a bearing assembly to actually hold everything together to keep it stable. So another issue here is that we can't have a potentiometer on the same axis. We need to have it on a parallel axis to the servo motor, and the way to transfer that movement is through gears. Either that, or we need to have a wraparound arm to hold the potentiometer, but then we run into different issues, so we're gonna go this route. Okay, so now you've seen how the modules look. There's one thing we need to address, and that's the last joint and the base joint. So the thing is, for these joints, especially on our arm, every single axis will be supported both by the motor shaft and the potentiometer shaft. Especially, for example, for this arm, the last joint was only constrained by the motor shaft of this servo, and that's too wobbly and it isn't strong. I've upgraded this by adding a bearing on the top. That's something I couldn't do down here because I would need a much bigger and more expensive bearing. So the proper way to go would be to use bearings. This is how bearings look like. They come in all different shapes and sizes, but the point of this arm was to keep it as low cost as possible. And again, this isn't a precision robot arm for doing precise movement. This is more for experimenting and learning. So I decided, let's see how hard it would be to actually make our own bearings with something that everyone has seen in their life and has access to, and that's marbles. So let's first take a look at how a bearing works and go from there. When we look at the bearing, we can see the inner and outer ring. The point of the bearing is that the inner and outer ring can spin at different speeds without any friction or with minimal friction. So we have the inner and outer ring, you can see the cross sections here, and I'm here describing how a ball bearing works. So it has little metal balls inside in a ball cage that just roll around, and that's what keeps everything constrained. For our custom bearing, I want it to be 3D printed, and instead of metal balls, I'll be using marbles since they're cheap and we can find them literally anywhere. But instead of having the cage, my inner ring will have small separating walls so that the marbles don't rub against each other and cause additional friction. And they will be sandwiched between two halves of an outer ring. So that's the idea for my bearing design. Okay, now that you've seen the drawing of the bearing, let's look at the design itself. I'll begin with the part of the outer ring. As you can see, it has this curved surface here, which is a bit over the diameter of the marble itself that we're going to be using. Besides that, we have the lower half. The lower half also has the attachment points to attach the whole robot to a base, as well as attachment points for the servomotor assembly. This is just a hole to insert an M3 nut inside. And the inner ring is the interesting one, is this. So each one of these sections is supposed to get a marble, and these here are the divider walls. And the point of them is to just not let the marbles touch each other, because when marbles start rubbing one against another, that's where you get actually the friction and the bearing won't work properly. Besides that, on the top of this inner ring, we have the section where the joint that you've already seen screws into place. And on the bottom, we have the holes for attaching the servomotor plate. So together, this looks like this. And then if we add the servomotor and the potentiometer, they go here like this. Of course, we need a way to attach them to the construction up there. So to do this, the servo is again going through the plate and attaches to the inner ring over this gear, and the potentiometer has the same gear, and all of that is held together by this servo mount. And this is how the whole assembly looks like. The same thing is done for the last joint assembly that you can see. It's just in a much smaller package because we don't need a bearing that big, and we also don't need a hole to run all of the cables through down to the box. Okay, so now that you have seen the concept and the design of the big bearing, let's see how it goes together. So it goes together using these 8 M3 20 screws. So the first thing is we need to get the base. The base is the one with all of the M3 nuts already inserted. I've already done that off camera, as you can see. These 4 holes are for mounting the servo on the bottom, and these 8 holes are for actually holding the bearing together. And these 8 holes here are for mounting the robot to the box, to a stand, or to whatever else. So the first thing that we need to do is actually put in the bearings, but we start by putting this thing in the middle. This bearing, as you've seen previously, uses 15 bearings. It was a bit of trial and error to get the tolerances right for the bearing to spin freely. So that's why we have this adapter ring right here. Okay, so everything is in now. Next goes the spacer. This spacer is 2mm thick. And on top of that we have the holding outer ring, so let's just screw it down. Okay, and just tightening the last screw. And with that, our bearing is complete. As you can see, we can spin it around freely. It doesn't have to spin freely as a normal bearing. The only thing it's supposed to do is when it's loaded to actually allow the servo to spin the whole base of the robot, which it will. You've seen how to assemble the middle modules, so now let's assemble the top module. One thing to note here is that I will be using some grease. It's not mandatory, but due to the bad tolerances of generally 3D printing and the marbles, I found that it works much better if you actually use some grease. So let's start by applying some grease using Q-tips. This is just some random automotive grease. Anything will work pretty much. Okay, so now we're done with that. Now it's time to assemble it. This here is the inner ring, let's call it that, and it's also the mounting plate for our gripper and things like that. This is the top plate, so to assemble it, this goes over here like this. And now we need to put the marbles into place. We don't need to put grease on the marbles, they'll get grease when we push them in. The tolerances are pretty tight, so they will pretty much click into place, as you will hear now. There you go. Next thing to do is to actually put the other part of the outer ring to encase the whole bearing. So just make sure to align these holes. The top part already has inserted M3 nuts here. So align it like that. Okay, now with that assembled, just spin the bearing around to get the grease on the marbles, and you will see that it will start spinning pretty freely. And also when you put in the motor, it will straighten the axis and make it spin even more easily. Okay, we can leave that to the side for now. Now we need to attach the potentiometer and the servo motor to the servo mount. Let's first do the servo. Okay. Make sure that the top of the potentiometer and the gear align. So let's just lift it up a bit, like so. Yeah, that's pretty good. And because the tolerances are pretty tight here, make sure that the gear doesn't touch any of the pillars here. Okay, now we need to use the Arduino Uno as we did for the previous section. We need to center the servo. So let's connect it up real quick. 0, 180, and that's 90 degrees now. Okay, so what we need to do now is actually center this potentiometer. As you can see, we can just put it at something like this. All we need to do, make sure is that it has 90 degrees this way, which it does, and 90 degrees this way, which it does. Okay, so we leave the potentiometer like this. Now, the only thing is that we need to align these 4 holes with these pillars here, so we can actually screw it down later. And just get the teething as best as you can. But, I mean, the potentiometer has much more than 180 degree travel, so it won't make a big difference. Okay, and now we just need one last screw, and that's the screw that attaches the servo plate to the servo motor itself. And with that, our top joint is complete. So that would be it for the whole assembly. The only thing to do now is to actually assemble all of the modules together. They are easily assembled using these holes here, or for example, these holes here on other joint pieces.
Do you like free stuff? You can join the Rotest program. You can get free dev kits, test equipment, and even online training courses. In exchange for a detailed review, join our Rotest program. Learn more at the link below. Free stuff.
That would cover all of the mechanical aspects of the build. Now let's get to the electronics. For now at least, I will be making a low-level controller, so just a hardware controller to run all of the servos. So I won't be doing any fancy stuff like direct or inverse kinematics, things like that. All I want to do is send G-code-like commands to a microcontroller and for it to actually move the servos to the actual angles. I will be going with a Raspberry Pi Pico W microcontroller, so the wireless one. It's the same microcontroller as the Pico. I just want to have the wireless capability maybe for some future upgrades. Let's take a look at the final schematic. So for the most part, it's just connecting all of the servo motors here on the left to the Pico, as well as all of the potentiometers. One thing with the Pico is that it only has 3 ADC pins on GPIO 26, 27 and 28, and we want to connect 6 potentiometers to that. So to do that, we're gonna use a multiplexer, the CD4053B by Texas Instruments. So we can literally switch between 2 potentiometers on one single ADC pin. So we can do that in software, and for the reading speeds that we're aiming for, this is more than good enough. The servo motors already require power, the 6 volts, and they also require the signal wire. The signal wire needs to be connected to each to pins 0, 2, 4, 6, 8 and 10. This is because we are using hardware PWM on Pico, and the PWM on the Pico is separated into slices, and we can control each slice independently. One slice is, for example, GPIO 0 and 1, so we can only use one of those pins the way I did it with the library. So this is how I connected all of the motors. Besides that, we have the power supply. I'm just using a adjustable linear regulator to drop the 6 volts to 3.3 volts. So this would be the end of the schematic, besides me making a mistake and not reading the datasheet, because this was an error I was actually looking for a while and why it didn't work. So this doesn't work, and the simple way to fix this is by adding this piece of circuitry. If you look at the datasheet for the CD43BE, the voltage at which we can actually trigger the multiplexer for 5 volt power supply is over 3.5 volts. So actually trying to do that when we are powered by 6 volts, nothing happened. So we need to step up those 3.3 volts to 6 volts, because we have 6 volts already, to be able to actually trigger the multiplexer. Let's solder this board now and test the robot out. Before we test the robotarm, we need to first program it, of course. Let's take a look at the code I will be using. So we will be using 2 libraries, not 3. My first test included the servo library, but I found it didn't work too good with this many servos on the Pico for some reason. So I opted instead to use the RP2040 PWM library, and I'm also going to use the Pico timer interrupt library, as you will see. These are all of the pins I will be using, and these are some of the parameters that you can actually configure for the robot itself, like the minimum pulse width, maximum pulse width for the servos, which is in the datasheets from 500 microseconds to 2500 microseconds for 180 degrees. So okay, let's jump to the setup function first. The setup function is pretty simple. We just start up the serial, define all of the pins, turn off the relay, which is important so the arm doesn't start going randomly. Make sure that it's actually off, configure the ADC, configure all of the PWM channels, and configure all of the timers. In the loop function, the only thing we are doing is checking if there is some command coming from the serial, and if there is, we are decoding the message. So let's look at that now. Okay, so this is just the check serial function. It's the default function for just checking if there's some data on the serial data line. So this is when we type into the COM port. That's how we communicate with the Pico. And let's go now to the decode serial message. These are all of the commands I plan on. Some of them I already added, and some of them I will be adding. So for example, C0 is the main command. That's the stop all command. If we see that the robot arm is trying to do something that it probably shouldn't be doing, we just type C0 and it kills the servo and all of the PWM signals, so the robot just starts. The commands we will be using in testing and generally, for the most part for now, are the C0 to stop all, C2 to turn the relay on, C3 to set a particular joint motor angle to a defined position, and C7 to set all joints to desired locations. So commands are pretty simple. Let's just look at the most complicated one, the C7. So it's in the G-code style. We start with the C7, which means this is the command that we are sending, and we just go A0 as angle 0 and type the value x0, which can be anything from 0 to 180, and we do that for each angle. And this is how we just parse the message out of the string. And depending on if you're in the ramp mode or not, we just send those commands. Now this is an interesting thing, as you will see later on in the testing. We have the update motors and the robot motors. What robot motors does is just send these angles straight to the servos and then let the controller on the servos do what they do, which it works okay, but the arm becomes too jittery. And if, for example, we go from 0 to 180, the robot arm can pick up a lot of speed and a lot of inertia, and these motors are just not that strong to handle those speeds. So with the update motors function, we just update the goal if you're in the ramp mode for each angle, and we can check that that's actually handled by a timer. Here we update the goal, for example J0 goal, when we update it to the new angle and check if it's not the same as the current thing we're sending each cycle of the timer to the servo, then we just increment it by 1 or decrease it by 1. Meaning that there won't be no jump from 0 to 180 directly, but it will go 0, 1, 2, 3, and like that to 180 at 100 Hz frequency, which gives a much smoother and slower movement to the robot. But also there's much less, while it is slower, there's less inertia for the motors to handle, so the whole movement works much better. Okay, so that would be the part of the code that works for now. I'm still playing with the playback and recording functions, so I hope I'll have them complete soon too. And here's the finished robot arm. As you can see, I've mounted the arm to a just standard 150mm junction box, so I can have a nice test stand, and I've added some feet that can mount to aluminum 2020 profiles. For the connections, I've just put an external USB connector here and a GX12 6-pin connector here for power, and later for I2C, as you will see maybe in some of the following videos. I'm really happy with how the arm turned out, but as you can see, one of the segments is a bit different. So during the testing, these segments with these servos turned out to be too weak for the arm this size. The arm would have to be even smaller and lighter, and with this heavy top bearing here, this motor especially couldn't handle that. So I made a little mount for the standard size servo that actually has a built-in analog feedback, so it worked out pretty good. But honestly, as you will see now during testing, this joint right here could also benefit from a motor swap like this one here, and it wouldn't add too much to an additional cost, but we could do something about that later. So let's go on and test this robot arm to finish up. So let's just activate the system. So for example, if we go and want to turn the base by 90 degrees, you can see how slowly it turns now. Or if we go 180, this also relieve a bit of the pressure from some of the motors, since they won't have to handle all of the inertia caused by the upper segments. So for example, if we look at the joint number 3 and put it to 0, you can see that the actual joint 2 can handle that, because the arm didn't just swing it fast, so there wasn't a lot of inertia. Or if we switch it to the other side, you can see the same thing, it works great. Okay, it also works when we do all of the angles at once. So for example, let's do the pose that we did previously. And as you see, it just goes way smoother than it would without the ramp limiter. I will be upgrading the second joint as well to a bigger motor, but for now this is just, yeah, as you can see, it can still happen, but it works much better. I need to upgrade to that motor as well. Thank you for watching, I hope you liked it. This arm is not up there yet, like this one here, but I'm gonna continue working on it. Gonna replace this motor here with the one like this here, and gonna finish up the software so that the recording and playback functions were great. My next goal for it for now is to add this attachment to it, which is a Sharpie mount for the top plate here. So when I use the end of the robotarm in recording mode and write something so that the robot can repeat it. I can then experiment with adding grippers and maybe even adding a Raspberry and running ROS and doing some direct and inverse kinematics. All of the files, codes and everything that I've used for this arm can be found on the link down below on Element 14 community. If you have any questions or comments, please leave them down below and I'll make sure to answer them. Until next time, see ya!